let's get started. Another day, another stream. So today I was going through a project called Luminal. I think I sort of talked about it in the past. I said I should probably be looking at this because it's really interesting. So that's what I'm going to be doing today. And I'm going to go ahead and keep this quite short because I've just started looking at it. Been too much work and lots of different things that I've been having to deal with. Now that I have some time, I can get to this. So what is Luminal? In the past stream, I think we've sort of talked about Burn, and I think we spent 3 different videos on it. How Burn does automatic kernel fusion and what's its architecture like. In fact, we can actually sort of just do a recap of that as well. So technically, whenever we talk about pretty much any deep learning framework, there's a particular flow that we sort of go with, which is if you take something like Burn or PyTorch or JAX or TensorFlow, etc., if you've been following these streams, you've probably figured out by now that you are actually writing either code in Python or in Rust. But code like Pythonic code or Rust code does not really run on, say, any accelerator like the GPU, etc. For that matter, none of the general purpose programming languages do run directly on accelerators. But you're able to just write whatever you want in PyTorch. You're able to do some tensor operations and then effectively leverage the fastest piece of hardware that you have for it, right? The way that works is, just to recap what we talked about in Burn, is you write your tensor operations either in Rust or Python or whatever. That is going to be, you take that and parse that and you convert that to what is called a compute graph or a computation graph or whatever people call it. People also call it op graph or operation graph, etc. Now, this is just a representation of your code, and I spoke about it in length. I said, these are all your ops probably, right? And Burn, we were talking about Burn's automatic kernel fusion, saying, you instead of having to work with 3 different operations, you could probably just club them and do one operation. Anyway, that was the previous one. But coming back here, what happens is tensor operations from which you generate a compute graph, from which you'll take that compute graph and you optimize that graph. And a lot of work is actually happening in this part, is the optimization part. How do you build the best possible, let's say, GPU kernel for a particular job? If you're writing a machine learning model, or if you're writing some LLM stuff, and you have a part of your compute graph, let's call that a subgraph. You'd like to really see if you can apply some optimizations and make that thing go faster, etc. Or deal with things like bandwidth, a bunch of different parameters. This is the portion that you'll be looking at. The moment optimization is done, then there's like a couple of things that people can do. I'll talk about it in a little more detail as to what the options are. So far, I've seen 4 different options. But basically, what Burn did is you had Burn came up with this idea of kubecl, which is its own representation prior to it converting or it producing what's called GPU kernels. So basically, you take the compute graph, the optimized one, and you are going to go ahead and trigger kubecl kernels, which are basically compile time specialized. Eventually, what they will do is they will go ahead and generate target-specific kernels. For example, if you're running on, I'm using the Mac, so I'd probably be using the metal shading language. In other words, I'll be using the metal backend that Apple provides. If you're using NVIDIA, you'll probably be using CUDA. If you're using something like WebGPU, you'd be using Web GPU shading language or Wixel, right? So Burn supports multiple backends, and I think we've seen that, right? So all the way from, tensor operations that are written in, written in any language like Python or Rust, etc. From that high-level abstraction, you need to sort of bring it down to the hardware that you're going to be working with, and you need to figure out what's the best possible way to write, to translate that into this particular, what you'd call kernel. So that, and by the way, I keep using the word kernel. It's basically a program that runs on the GPU. I think I've talked about it quite a bit, so by now you should probably know that. Yeah, so this is probably the structure, and where Burn sort of differentiates itself is, in this part, this optimization stuff and the kubectl stuff and its own IR and doing quite a few things, etc., which is great. So as I said, everybody, or rather most folks, are focused on the middle part. Everybody's going to be focusing on trying to come up with something new in that space, and that's Burn's thing. Now, if you were to look at, let's say we looked at this new thing that I was talking about, which is Luminal, right? But before I go into that, let me give you a visual view of what that would look like. So let's say I go ahead and, I just put some, what you'd call op graph, an operation graph, or tensor operation graph is what I want to put together. So I write it this way in PyTorch. I'd say, okay, go ahead, start with, an RMS norm, give me a query key value, whatever, and then do an attention on that, and then do a projection on that. These are all operations, like you see over here, okay? They're all operations. So these operations are ordered. There's a sequence in which they appear, that is. The same thing Burn does. So Burn and PyTorch both are full-fledged deep learning frameworks, in the sense you write your code in this manner, which is you think about it in terms of tensor operations, and magically that gets translated to the hardware that you're going to be working with. In our case, the hardware is usually the GPU. So you write it in this form, then you generate this compute graph or op graph or whatever. And then I talked about 4 different ways to generate basically code for your hardware that your hardware will understand and run in the best possible way. That is performance, efficiency, whatever. Lots of different parameters, right? So predominantly, the first way that you can think of is, I forgot to include this, but this should have Apple Metal MPS. Apple has a library called Metal Performance Shaders. Now, it doesn't supply the source code for that. Apple's very, very sharp about that. I don't know why you would want to hide that. Anyway, so there's Metal Performance Shaders. Similarly, NVIDIA, which is the big juggernaut over here, they have a bunch of different vendor-provided libraries for different kinds of work. You have cuBLAS, cuDNN, cuwhatever, a whole bunch of different things, etc. So one option is you can try and basically look at the operation graph and then, leverage these vendor-provided libraries directly to go ahead and, produce GPU code and then have your tensor operations or your graphs run on the GPU. Then the second one is what I'd call custom kernels. This is where Burn sort of falls into this particular bucket, where what we're basically saying is you are going to be generating kernels that are custom, depending on, your entire codegen pipeline that I just showed you. It sort of looks at all of that and comes out with that. And then before I go to AI generated, because there's very few players over there, there's compiler generated stuff. Now, this stuff is a little different in the sense, yeah, it's a little different in the sense that, these guys use what are called multiple, for example, IREE is going to use, it's IREE is the name of the compiler. It's basically uses MLIR at the back end, does multiple levels of lowering, and then produces a kernel. I'd sort of fit that. So custom kernels and compiler generated stuff, they are sort of, there's an overlap over there. A kernel can be generated either by the compiler or, a person can actually write it manually. So you go figure, whichever one. And then there's AI generated stuff where you basically ask AI to help you write code. And that's, I think there's a company called Alpha Tensor. I think I looked them up, and I presume I haven't looked at what they do, but that's one option. And then there's, so Luminal effectively sort of again straddles with this particular part, custom kernels versus compiler generated stuff. It falls into the same bracket, but it has a very, very, very unique proposition, which is very intriguing to me. The first thing that I love is the fact that, they keep using this word, which is simple, right? We want to be minimal, but being minimal does not mean that I trade off performance, right? So that's not something that they want to do. And I was really intrigued by this, and how would you go about doing this? And lo and behold, they actually are using some concepts that I've sort of touched upon in the past. I'll get to that part, what that is. But effectively, according to at least what their documentation is saying, I see that everything in Luminal boils down to these 12 primitive operations. So that's it. They don't have like 1,500 different operations that PyTorch gives you. None of that stuff. So they'll use this as the foundational elements, or rather, primitive operations, using which they'll build, the more complicated ones. So if you notice, there's no MatMul as well. So matrix multiplication is the essence of what machine learning is. Even that's not here, because the way they are modeling it is you do a multiplication, a broadcast multiplication, and then you do a sum reduce, right? I'll show you both of them because I was sort of going through this as well. And I noticed one thing that I really like about this. It doesn't take you very long to sort of just look at this repo and say, oh, I get what you're doing, right? Of course, I'm going to get to the part where, the magic that they have, the stuff that's unique to them, which is what's called, they've mentioned it, search-based compilation. It's an interesting phrase. It's basically a mix of what you'd call searching without any deterministic pathways being taken, etc. You're going to go for search, a regular search, but doing it a little more. They're going to be using some concepts that are interesting, along with when you search for something, you go ahead and auto-tune that and see whether this is the best thing, right? I'll show you a nice little demo that I looked at as well. So let's, let's just start with that. Maybe that's a good segue to sort of get us started and look at that. What did I do? Oh yeah. So there's a demo according to, so this is basically the repo. And you can go ahead and, so there's a bunch of crates. We'll come to this part. There are examples, which is what I've been tinkering with. And then there is these demos. So there's this MatMul demo. And if you pull the demo up, you will see, okay, wait a minute. Yeah, I'm going to sort of, I'm not going to be writing anything, so you'll see my face. It's okay. So basically, this is the MatMul demo. Instead of me talking about what's going on, I'll just show you what happens, how does their thing work? So if I run this, I think I've already run it, so it should be fast enough to get up and running. So yeah, so this is a metal kernel that performs matrix multiplication. Whatever, there's a matrix between, there's two matrices that they want to multiply, which is 512 by 512, both of them. And this thing is basically going to go ahead and go through all the options. It's building a search space saying, what are the possible equivalent, what you would say, kernels for this particular problem or for this particular task. And in that search space, which is the best one? All right. So you see where we're going with this. This is an interesting idea. I think it's an intriguing idea more than interesting. All right. And plus the fact that they're focused on, let's leverage this stuff and make the entire framework much simple. So those two are really good combinations. All right. So you see that it's sort of, the graph is being looked at. Yeah, this is the amount of time it's taking, and you're pretty much going through multiple options. And yeah, you found it. You found some option that is probably the best. So it takes about 7 milliseconds for this to do a 512 by 512 matrix multiplication. It's using this grid, it's using this thread block. All these are important if you really want to produce the most efficient, performant kernels, because the number of parameters that you'd have to look at to do that job is pretty large. I think somewhere I read this where I think the authors put it really well. Was it here? Okay, wait a minute. I think I looked at it in the docs. Docs. Yeah, so I was going through the docs and I was going through the introduction. Yeah, right here. Oh, why? Sorry, the Y part. All right, so yeah, this is what I wanted to sort of highlight. So you're building a DL framework and you have a whole bunch of devices that you probably need to work with. You've got GPUs, TPUs, NPUs, whatever the PUs that you want, you've got all of them. And then most of them support different kinds of data types, basically floating points with different precisions, different precision. And then you already saw the operations that this particular framework supports, which is only 12, but you go to PyTorch, there's like 1,500 of them, right? That's actually, yeah, you'd actually have this level of permutations and combinations. That's device times, data types times operations. You actually would, if you're trying to build something that is a framework, that is, right? And being simple, intuitive, but not giving up anything on performance is a very, very intriguing idea. All right. It's an extraordinarily intriguing idea, at least to me, because I've been thinking about this for a very long time. I'll talk about what I'm thinking about, but when I'm ready, that is. But this is a very good idea at the face of it. So yeah, so that's the background for Luminal and why I thought it'd be a good idea to sort of jump in and look at it. Okay, so the first thing I did was, now with that out of the way, the first thing I did is I went ahead and obviously we ran the demo, so that gives you an idea of what you should be expecting. But the next thing I did is, as usual, go look at an example, see how this thing is built. And I started messing around with a couple of things. But yeah, this was not originally 50 million or whatever that is. This was just 5. So we'll look at both of them. Actually, you know what? Let me bring that down to 5. Okay, so the first thing I want to talk about is, as you know, so I've made some notes. Now, given, this search thing could take a little bit to sort of cover, I'll actually make that a part 2. But just to look at the architecture of Luminal, let's sort of look at that, how it's made up of. The first thing you should know by now is, if we're going to be talking about deep learning compilers, you are going to be talking about modeling or providing some sort of data structure that models the compute graph, right? And they have one, which is called the graph. Although I think they should have called it the compute graph. But anyway, so a compute graph, if you've seen this, where did I put that? Yeah, if you've seen this, it's not very clear over here. I'll show you. And the other thing about this particular repo is, I really love the visualization that they've paid attention to, because when you're dealing with something like this, it makes a lot of sense to sort of visually see what's going on. Of course, it gets complicated when you start looking at large models, etc. But when you're looking at, it is still a very good idea to get started with. And that's the best way to get started with, at least. For anybody who does not know anything about this, if you just give them a visual picture of, what does a compute graph look like? It takes away 50-60% of your questions that you might have. At least that's been my observation. So anyway, I'll get to that part. So let me just explain this example. It's pretty straightforward. You have a random number generator, and then you basically generate about 20 different elements, and you put them in a vec, and calling that a weight. And then you create your graph, which is your compute graph. You actually create one, and then you go ahead and start, adding operations to it. So operations become nodes, and the edges between them become, the edges connecting those operations to other operations become inputs and sort of outputs and stuff like that. So you take the weight that was created over here, and you create a linear layer, and you set the weight of it. What is a linear layer? Not to worry, you just go look at it. This is what a linear layer is. It has a weight and a bias. Okay, a weight is some matrix, a bias is also some matrix. just know that much. Here I'm creating a linear layer, which is 4 by 5. The way they say this is 4 by 5, but just know that it's 4 rows and 5 columns at least, because this thing uses row major. The format, that is. The rows come first, columns come second, so 4, 5. And then we set whatever weights we've created, we'll sort of set that here. And then we go ahead and create a new tensor. In this case, any of their tensors that you create that sort of are going to be added to the graph, they're calling it a graph tensor. I think that's the definition that they've given as well. A tensor on the graph. Yeah, that's it. So this one's 4. That means it's just a single dimension. It's 4 elements in there. And then linear layer, you will have this concept of forwards and backwards. I've discussed that to death. I'm not talking about it. So you do a forward, and then you're going to go ahead and just pass in A. So if you notice, up until this point, none of this is actually, so when we say model.forward, nothing really happens. This is all lazy stuff in the sense, as I said, like Burn as well. You don't immediately go ahead and do, the addition or the multiplication or any of that. So it's using the lazy method. So, and then we come here. We see you call compile on your graph. So your graph was here, and you call compile on the graph, and then you say, what kind of compiler am I going to pass in, so that you're going to go ahead and compile it. Compile the graph using the given compiler. So I've put metal over here, but you can actually, again, just like Burn, where I talked about composability quite a bit, here there's a composable design again, where you can say, okay, do this first using this compiler, run these optimizations, that is, and then pass it on to the next one, pass it on to the next one, pass it on to the next one. So let me just show you what that means. So I could just say, yeah, generic compiler. And so if you go look at the generic compiler, this is actually a tuple, right? It has like 4 different compilers in it. Actually, these are not compilers. I mean, it might be a little confusing, but it's actually a good idea to call them compilers. I think so, because that's kind of what they're doing. These are passes, in the sense, optimization passes. So one's going to do remove unused nodes, which is basically dead code elimination, or DCE. Another one is arithmetic elimination, like redundant arithmetic operations, just pull them out. For example, x times 1. That's stupid. You know it's x. So reciprocal of some, say, reciprocal of some x. That's just the same thing, right? As x. Then CSE is interesting, where we talk about common sub-expression elimination. That's a very specific kind of optimization. So you'll see that, you'll basically implement the compiler trait for that. And then that optimization is basically now a compiler pass, right? So generic compiler applies those generic optimizations. They make a lot of sense. Now, the idea is you do 1, 2, 3. That is, for example, you do this, you do all of these things in sequence, you do all these optimizations in sequence, and then you move on to Metal compiler. And then when you go check Metal compiler, it again is a sequence of optimizations that you can apply. Like the first one is Metal compiler pre-buffer. The non-buffer stuff is what they're talking about. If you come here, there's some primitive optimizations that you can handle with this, and there's some special optimizations in which you will see a bunch of different things. You will also see the MatMul thing over here, right? So this is the composable design that they've sort of put together, and the idea is this. This was the fastest I picked up a project, and I said, yeah, I think I get what you're doing. That's big. That's really, really big, if you ask me. In today's world, whenever you talk about, just go deal with PyTorch, see what happens. You'd be pulling your hair in a couple of things, saying, okay, how do I fix this? How do I do this? How do I understand that? What exactly is happening here, right? There's a lot of nuance involved. Now you might be saying that, okay, yeah, this is a pretty new project, so maybe you're probably right. But the design of it is what gives me hope that I think this is heading in the right direction, right? So those are my thoughts on this. Anyway, once that's done, once you've compiled your graph, so basically you've said, okay, here's a linear layer, or here's some bunch of tensors, and then there's another tensor that I created, and then I say forward. And what does forward actually mean over here? If you go look at it, forward does a MatMul, okay? Just sort of keep that in mind. It's not important what a linear layer moves from how many dimensions to how many dimensions. That's all, AI speak. But anyway, so you've got that, you've compiled your thing, and then you can display your graph. The point is, you've not executed anything. Execution has not happened. And I can just display this. So for example, if I go ahead and sort of run this, great. Let's go. Yeah, so it's running. And yeah, I need to take my face out of things. Yeah, you can see this. So this is what we get. This is exactly what's happening. So you're allocating a bunch of metal buffers. You're loading your tensors. In this case, there's a weight and there's another tensor, which is A. You saw both of them. You'll need to copy them to the device, right? So in GPUs, when you're doing copying, that is both in and out of the device, that's also an operation. The GPU must be doing that. Of course, it's not going to be using any of the compute stuff to do that. It's going to be using some DMA engines to do that, etc. But this copying is still involved, right? So you do that, and then you're going to go ahead and call metal kernel MatMul. This one, I feel like they should have changed the name over here because it does something a little different, where you actually generate the MatMul kernel is what I was able to understand. And then finally, you go ahead and call this operation, which is execute metal kernel. So this is where I believe, if you remember the metal API that we looked at, the Vulkan API that we looked at, etc. You start off by saying, okay, here is a device. Here's a command queue. I'm going to submit command buffers from the host to the device. And then when I'm done, I will say, I'm done. Please go ahead and submit this, or rather commit this to the command queue. And then I'll wait till your response comes back. I won't be sitting there waiting. I'll just go do something else. And once that's done, once I get it back, I'll copy the result from the device. Although this is the simplest way to visualize what that code is. So whatever you saw over here, is basically this, right? It makes it a lot easier, right, to think about it this way. If you're looking at it and you're saying, oh wait, this makes more sense, right? So yeah, I'm not going to go cover the entire, what's allocate metal buffers, etc. I think some people may have questions about it if you're new to this particular stream. I've covered that in previous streams. You could probably look at them. Something like the Vulkan stream that I talked about. Here it's not Vulkan, it's metal, but the concepts are pretty much the same. It uses a similar API. Okay, so once that is done, you're good. Now, the other thing that you should see is this. Whatever happens here, which is execute debug, that is the place where you're actually going to go ahead and launch your kernels and have them run on the GPU and get your response back. All that stuff is sort of happening over here, and they're also well timed. Now, this is not like what you'd call exact timings. These are what I'd called approximations, because they use things like, it's just a time instant thing that is being used, and not much over there. So, but they're pretty good. I think they work. That's what I'd say. And you can see this. You'll see that the reason I think this particular graph makes a lot of sense is you'll see that, okay, these are the nodes, whatever is circled. I think we could probably have a better, more visually appealing diagram. Maybe that's something we can do. But basically, you have, you see these indices over here. This is the point at which one of these nodes or operations was added to the graph. So probably the first thing that was added was this, then 1, 2, then 3, right? Which is what you'd see here, same thing. And then 4, 5, 6, 7, right? So this is kind of interesting. It's not necessarily in the same order that you'd expect it to be, but it's pretty much in the same ballpark. So that's one. The other thing that you could also check is to see, okay, what optimizations happened over here. Now, considering what this kernel is, there's no real reason to optimize anything over here. It's just a straightforward kernel. You're just doing a MatMul, That's it. There's nothing over here. However, the first demo that I showed you, that demo was searching the search space for pretty much every single, what you'd say, option. What are the possible kernels that I could be using, which means what are the possible parameters, like the grid of threads, the thread block sizes, all of those pieces. What are they? What can I be using, right? So that's not this, in the sense that when you do this over here, we're not actually using the entire the search-based compilation thing. This is still using the primitive optimizations, as you saw, CSE and dead code elimination, all that stuff. That's all regular stuff. Search space compilation or search-based compilation is something that there's a different example for that. I probably do that in part 2. But yeah, just know that this is happening over here. When you call execute, that's when you pretty much do the work, right? So yeah, so that's kind of what I wanted to talk about, which is they have a graph in which you store this is basically the storage for everything, okay? And you store your tensors, you store your ops, blah, blah, whatever. And we already saw graph tensor, which is basically anything that, any operation that's using a tensor as its input or output or whatever, that becomes a graph tensor. It's a tensor on the graph. That's what it means. All right. And then this stuff, which is the search-based compilation, etc., I will talk about it later. But just to give you some idea, what is basically going on is they've come up with a nice idea where they're going to be using e-graphs. Now, if you remember e-graphs, I sort of talked about it in some detail when we talked about crane lift, the other Rust backend apart from LLVM, where you can basically take crane lift IR and produce machine code for a bunch of different target architectures. Over there, they use this domain-specific language called ISLE, which is instruction selection and lowering expressions. And that's the first time that I came across what's called e-graphs or equality graphs. Now, the idea is pretty simple, okay? And I sort of talked about this, where we're saying an e-graph is basically like a data structure. It says, I hope you can see this, or should I just make this bigger? Yeah, I can do that. So let's say, and I think this is documentation that I've taken from the crate that I believe pretty much everyone's using right now. It's called egglog is the name of the crate. So this is a very good picture. And I said, that's what visualizing something is much easier when you're talking about these abstract concepts. So think about it this way. When I say 8 times 2 divided by 2, if I want to represent that, I could sort of represent that with something like this, right? I'd say, let me have a sort of a graph structure that says 8 times 2. And then whatever is the input over here that comes out of this particular block can become the input over here. So whatever this expression is by 2 gives me this. So you'll have E classes and then you'll have E nodes. Okay, great. That's the first thing. Now, the thing about E graphs is it's the most memory efficient way to sort of figure out equivalent expressions. That means if I come across something else, some other expression, I could easily sort of, include it in this data structure in such a way that, yeah, if these two expressions are equal, then I can store it very, very compactly in this data structure. All right. So to give you an example of that, an operator takes as its general, not other operators, etc. That's not interesting to me. Let's look at the picture again. So you've got this. This is 8 times 2 divided by 2. Great. I could also write this like saying 8a left shift 1, and then the same thing, right? Now, so previously this thing was the E class, right? Now you can have another E class that represents both a times 2 and a left shift 1. They both are equivalent expressions, right? That is what an E-graph is trying to do. It's trying to come up with equivalence relationships between expressions. And the way it does that is by rewriting the graph, right? So the final rewrite that, like, for example, this is it. Now you move to the last part. Okay, that's not the last part. But you can keep going forward. Like, you can expand this particular graph to also include something like this, maybe this particular expression. So if you say x times y divided by z is x times y divided by z, the same thing. You can do that. So you start building up an E-graph, an equivalence graph of terms that are equivalent. And you can do that in a compact, without taking up, lots of space, etc. So this is basically a very, very efficient data structure to represent equivalence relationships between multiple expressions in a very compact manner. You can definitely read about it. At some point, what happens is once you keep growing, so they call it growing this graph. You keep growing the graph, growing the graph, trying to say, okay, this is equivalent to this, this is equivalent to this, this is equivalent to this. And at some point, you're going to reach what's called equality saturation. All right. For that, it's not straightforward. You'd have to come up with a cost model, etc. Those things are all extra. But the basic notion is this. That's it. It's a data structure that represents equivalence relationships between terms. And it's composed of things called E-classes and E-nodes. So what the Luminal folks are doing is, if we go back, okay, what the Luminal folks are doing is they're basically taking their graph. They have all these different, combinations in which those graphs can exist. They're going to keep, again, doing their rewrites on top of that and trying to figure out the search space for the possible equivalent kernels that they can produce. And then they keep testing each one of them to figure out which ones are the best. That means what's the best that I can get to. So obviously note that which ones are the best has to have some cost model. You need to stop at some point to say, okay, I'm done looking at searching. I'm done searching. In order to get to that, it's not just, the compiler is magically going to go ahead and search the entire space. This is not solving, this problem that search is infinite, technically. All right, that's not what it's solving. It's just making things a lot easier in terms of how you would go about writing code and figuring this out, right? Okay, so that's kind of what I want to stop with search-based compilation, because I do intend to go into a lot more depth over there in the next stream. For now, I just want to look at the structure of Luminal as such. And then here's how you do some rewrites, some of the stuff that I was going through. I'll talk about this. This is, again, very much like IL. So if you've seen IL, the language looks crazy. It's based on Lisp. Here, this is also going to be based on Lisp. So good. Right. I already showed you the visualization capabilities, which is what I really like. I'm still trying to figure out how do I look at the exact kernels that are generated. So that's something that I want to look at. So the first one that you saw, which is we were doing the MatMul demo. That is actually using the search-based compilation stuff. And that thing prints out a kernel. But in general, if I wanted to look for a kernel for this specific example, I'm just trying to figure out how that works. I know they've got some, what you'd call, what is that? Yeah, they've got this particular debug environment variable that I can just pass, which tells me one thing, which just tells you that we didn't do much optimization because there's nothing to do. It's a pretty straightforward thing, right? So you'd get this kind of stuff, but I'm still trying to figure out how do I get just the full matrix multiplication. Here's the other thing that I also wanted to show you, which I think before I lose track. What if I just go ahead and ran it with the generic compiler stuff? Now that stuff runs on the CPU, so you'll see a different graph. Yep, let's run that. So this is what you would see. Yep, this is what it looks like. There's two tensors. There's a matrix multiplication and there's a reduction. And this is what I meant by saying that this stuff, which is a matrix multiplication, is actually composed of a element-wise broadcast multiplication plus a sum reduce. They sort of clearly use that. They use their primitive operations to build this graph for you. And that's kind of what's happening over here. Okay. So yeah, so you can do pretty much write any model with just the primitive operations. I don't think Luminal is the first project to talk about that. TinyGrad and a bunch of different other projects have sort of shown that it's most certainly possible, and you should probably be doing that. And I think in the long run, simplicity is definitely going to win over complexity, and I think this is a good strategy for that. Right? Okay. I think we're going to sort of go in too much time. I don't want to take up so much time. So let me just minimize that. So we talked about the architecture overview. Luminal has a lazy architecture. Luminal constructs a graph, and that graph is optimized. There's primitive optimizations, then there's a search-based compilation optimization, which we will touch upon. And then, yeah, this is the MatMul thing where I was talking about element-wise broadcast multiplication, etc. So I actually did want to show you something. Let me see if I have time, but just let me see if I can just, yeah, let's not go into all this. This is pretty straightforward. Why this approach? Well, this is how, a traditional compiler, this is the traditional way to think about matrix multiplication. And if you know that these two operations make up a MatMul, you could probably go ahead and figure out a way to fuse that and say, okay, give me the best implementation of this. So those things are available. Yeah, and I already talked to you about the compiler stuff, the way it's composable. That's pretty good as well. And not much. The compilers use this tuple design where there's simple macro rules to implement the compiler trait for each this thing. That's okay. Yeah, I think this would be interesting. Let me go back here. So for example, let me just do this, and let's say, wait. So if I do this and I say, if I just show you this, I just want to show you one of them. At least one implementation should be good enough. So basically, any operation can become what's called, I'd say, a compiler. So in this case, just think of them as optimization passes, because that's much more simpler. This optimization pass, which is MatMul compiler, if it just implements the compiler trait, you're done. All right. And then there's the kind of optimizations that you would see over here are things like, you see, you're going to select, you're going to say, okay, a metal subgraph is over here, and then it's not a subgraph though. I would say, let me just look at this. There's a way that I've sort of framed this. Okay, so yeah, I just put this over here. So let's look at that. So the thing is, Luminal is using this concept of a select graph and a search graph, etc. Now, this is not exactly related to the search-based compilation thing. At least that's what I think. But this is basically a pattern matching tool. So it's basically going to say, I'm going to look for sequences that I know are optimizable. And once I look for them, I will sort of search for those sequences in my graph. If they exist, I know what to replace them with, right? It's kind of what is happening here. So for example, just take a look at this. Look for metal multiplication is what this particular part is. So we look for metal multiplication. If it's there, great. We also look for a sum reduction. If in this case, if it's there, great, which is what we're trying to do here. But the moment we do both of these, we would want to go ahead and search for that. That's what the search thing does. So what we're essentially saying is, we're going to look for very specific kind of patterns. And the way we look for those specific kind of patterns is, we want to look for these, this particular sequence of operations maybe, but each operation should probably be having this shape. And, say if you have a mul operation that is followed by a sum reduce operation, then we know that's a MatMul, right? If you know it's a MatMul, then we'll try and look up what's the best way to sort of replace that with something that's the most efficient implementation of sorts, right? That's kind of what this, which is what I'd call the primitive operations, or not the primitive operations, but I'm just going to call them the non-search based stuff, at least the non-egraph based ones, optimizations. These are, right? So that's good. So that's how far I've sort of managed to sort of look at the repo and make sense of things. But I will say this at the outset. This is extremely exciting for the direction that it's taking, right? Now, this is kind of what, we should be looking for more. We should be, getting more of this in the Rust ecosystem, where we're looking for ideas that are simple, but yet very powerful, right? That's kind of what I've been thinking about a lot as well. Okay, so that's what I actually wanted to cover. This is just, me having had some time, very little time, to sort of look at this and say, this is a very good idea, and we should, sort of talk about this. Personally, I'd like to sort of keep myself abreast about things that are happening. And I think this is one cool thing. Additionally, if there are any questions, etc., do let me know. Or if there are any thoughts about this. And if any of the folks working on Luminal are watching and I got something wrong, please let me know so that I can correct it, at least as a comment, so that people know that, I'm not talking crap. Anyway. All right, that's about what I had. I think I've sort of overshot as well. Anyway, I hope this is useful. And it's been pretty useful to me just going through the code base. All right, that's it. Thank you and have a good day. Bye-bye.